Okay. In the last class, I showed you how to run exploratory fact analysis, the fact analysis using R, using this example, right? So we have 20 items in this case. So for this example, I used the items, but you can also use your variables, right, for the fact analysis. But for this example, I just used the 12 items to measuring 4 different constructs. Okay, so our job is to find the structure, the construct structure of these 12 items. So and then this was our the main question. So that we're gonna decide the number of factors to be retained, and what would be the total variance explained by these factors, and to identify variables in each factor retained in the final solution. And also we will give names to each factor retained on the basis of the nature of the variables. So first we checked correlations, right? So the checking correlation is always the first step before you run the PCA or exploratory factor analysis. Okay, if you don't have a strong correlation among items or among variables, you can't expect the good result for your the fact analysis of PCA. Okay, so because basically these analyses are based on the correlation metrics. So okay, based on these results, that we can see fairly high correlations, right? So we can see dark blues, and there are very clear patterns. And then next you can test Bartlett test and KMO test. It's the Kaiser-Meyer-Olkin factor test. So do you remember what was the Bartlett test?
Homogeny of variance.
Yeah. So I mean, so this is testing the identity matrix. Okay. So our null hypothesis is identity matrix, identity correlation matrix. That means our identity correlation matrix, so the covariance among variables are all 0, right? That is our null hypothesis. So that is identity matrix. So for example, if you have a 3 variable, so x1, x2, x3, so diagonal should be 0, 1, and then orthogonals are all 0. This is identity correlation. So this is our null hypothesis, right? We want to reject this null hypothesis. If we reject this hypothesis, that means we have enough correlations among variables, right? So based on our result, we reject this hypothesis. That's a good sign, right? And the next, you can evaluate the KMO. These are KMO is the common variance of each common variance of each variable. So for example, this is 0.89. What does it mean? So this item, total variance of 89% of this item is explained by the common variance. Okay, so this one is 79% of the total variance is common variance. So we want high covariance, high common variance, right? So overall, their common variance level is a 0.87. So that's high, that's pretty high. So usually we want to, our common variance is greater than 0.8. Okay, this is a good sign. So this is a preliminary analysis for your exploratory fact analysis or fact analysis. Okay, so okay, based on these results, we are good to go with the fact analysis. And then we ran a 1-factor, 2-factor solution, and 3-factor solution, and 4-factor solution. Before we evaluate these 4 solutions, I ran a eigenvalue first, right? So based on my key, so right here, eigenvalue. So we can test using correlation metrics and test the eigenvalue, right? And then our eigenvalue is right here. So these are our eigenvalues. We can see very high eigenvalues for the first 2 factor. So that means probably the 2 factors that will explain the most of the common variance, right? And then you can plot the scatter plot right? So this is script plot. So we need to find the elbow point. Here is the elbow point. So from the, that means the first factor, so this is the first factor. First factor has eigenvalue of 4 point something, right? 4.8 something. And then this is the eigenvalue from the second factor, right? It dropped and dropped a lot. And then it start to flatten, right? So this is our elbow point. So are we going to select the three factors? Maybe three factor. Third factor has a pretty low eigenvalue. Its eigenvalue is less than 1, right? So our rule of thumb is eigenvalue over 1. So if the if the eigenvalue is less than 1, that's not a good sign. Okay. So let me go back to, and then I just ran 4 different models, right? So first factor, second factor, third factor, and fourth factor. I ran 4 different models, and then I added a core var equals false. That means I'm going to use correlation metrics. And then I used oblique the rotation method. That means that it allows to co-vary of your factors, right? So it allows the rotation below 90 degree, 90 degree, right? And then we're gonna use principal axis factoring, right? And then let's go back to our source. So do you remember what was the rule of thumb for the good factor loadings?
0.4.
0.4, right? We want our factor loading is greater than 0.4, okay? So that means, okay, look at this. This is the factor loading, right? So 0.255, that means the relationship between correlation between the first variable and this factor is 0.255. It's pretty weak, right? That means this variable is not very highly correlated with this factor, right? We don't like this one. This is pretty low. This is pretty low, low, right? So maybe the one factor solution may not be ideal. What about this case? This is factor loading, right? So do we have a two factor, but first variable is highly loaded on the second factor, right? Not first factor. And the second variable highly loaded on the second factor. And the third variable is the first factor. As you can see, we can have very clear two-factor solutions, right? So variable 1, 2, 5, 6, 7, and 12, they load on factor 2, and variable 3, 4, 8, 9, 10, 11, 12, they load on factor 1. Okay, so these 6 items are measuring the factor 1, another 6 items measuring factor 2. Okay, and then we can see the third factor solution and fourth factor solution, you can interpret in the same way. Okay, so for example, so in here, so this is pretty high, right? So this is pretty high and this is pretty high. So you can evaluate the same way for different factor solutions. Right? But sometimes you may see some cross-loaded items, cross-loaded variables, right? So for examples, let's say this is a 0.4 and this is a 0.4 and this is a 0.2, right? That means this item, this variable is not clearly classified as a certain factor, right? So contribution is pretty similar. This is a 0.4 and this is also 0.4. So we don't know these items belongs to which factor. So this is called cross-loaded variable. Okay.
Phil, I have a question.
Yeah.
So let's say in a case where we get a negative 0.5,
Negative
Uh,
0.5.
could we, would it be, is it tradition to like say, okay, this is a reverse coded item
Uh-huh.
for that
Uh-huh.
scale?
Yeah. So for example, let's say this is a 0.8, okay? 0.855. So that means this item, this variable is strongly loaded on the first factor, but the direction is opposite. So that means this item or this variable has a reverse relationship with this factor. Okay. Does that make sense?
Yeah.
Okay. Does that answer your question?
Yeah, I just didn't know if people commonly do that or they try to make a like negative factor, which they expect all those negative items to load on, as
Mhm.
opposed to like reverse coded items.
Yeah. So generally before you run a EFA or factor analysis, so you reverse code first, and then
Okay.
run factor analysis for the easy interpretation,
Okay.
right? So, but I mean, if you don't reverse code, you will see negative sign when you're factor loading. Okay, so and then now we tested, we plot the screen plot using a two-factor solution. Okay, so now we have right here and the big jump, big drop, and another big drop. And then from here, so this is the factor 3, but third factor's eigenvalue is less than 1. It's pretty low, right? So maybe we don't retain the third factors, so we'll get the 2 factors. Okay. So then let's interpret the results. So this is a factor loadings matrix of your R package. So factor analysis using method PA is, that means we use the principal axis factoring. Okay, if you use maximum likelihood estimation, you just put them ML here. Okay, so I use the principal axis factoring and FA data and number of factors of a limit and the correlation matrix PA. Okay, so this is the standardized loading. Okay, so it is called the pattern matrix. So pattern matrix is based on the correlation matrix. So this is the standardized loading. So each loading can be interpreted as correlation. Okay, so let's look at, this is the factor 1, the factor 2, this is the factor 1 and factor 2. So first factor loading of factor loading of the first variable is 0.73 on the second factor, right? So how can we interpret this? The correlation between A1 and second factor after controlling for F1 is 0.73. Okay, does that make sense? So the correlation between, oops. Oh, what is that? Okay, erase. Okay. So the correlation is a unique correlation. It's more like the partial correlation, right? The correlation of the variable after controlling for the third variable. So this is, okay, this is correlation. And then this is another correlation. What is this? H2 is, this is communality. Okay, so communality is 0.54. So how can we interpret it? So 54% of the first variable is explained by these 2 factors. Okay, and what about this? This is 74% of the total variance of variable 7, A7, is explained by 2 factors. Okay, this is communality. And then communality is lambda 1 squared times lambda 2, right? This is communality, right? So that means 0.01 square plus 0.73 square is 0.54.
Phil, I have another question.
Sure.
If the rotation were an orthogonal rotation, would the loading not be controlled? Like, so you're not controlling for the variance of factor 1 and factor 2 because it's like forced to 0, or do they? Does that make sense?
Can you repeat your question again?
So you know how you interpreted that 0.73 as the relationship between factor 2 and item 1 when controlling for
the first factor.
Yeah.
Yeah.
If the rotation is orthogonal, there's no controlling for.
No, I mean
factor
the interpretation is the same.
Okay.
So this is basically the standardized loading. So the loading is basically the coefficient, regression coefficient in the regression model, right? The factor analysis equation is the same as the regression coefficient. So when you interpret your regression coefficient, you can interpret it as the relationship between the first variable and the dependent variable after controlling for other variables, right? So interpretation is the same. So this should be, I mean, regardless of which the rotation method you used. So if you get a standardized factor loading solution, so will be same.
Okay.
Okay. Okay. And yeah, this is commonality. And what is this? This is the U square. Actually, this is U square. This is error variance, specificity variance, error variance. Okay. So what is total variance? So total variance should be 1, right? Because we used standardized loading. This is correlation matrix, right? So the total variance should be 1. So 1 minus our commonality is error variance, right? So it's 1 minus the 0.54 is 0.46. Okay. And what about this case? Let's look at this one. So 71% are explained by 2 factors. That is our commonality, right? And then this commonality, 1 minus this commonality is error variance. So this is error variance, the 0.9. Okay, and this is the factor loading. This is the factor loading. So if you square it, 0.85 square plus minus 0.06 square, you will get 0.71. Okay. So that means high factor loading, okay? High factor loading leads to higher commonality, right? Because the commonality is the sum of squared factor loadings, right? So if you have high commonality, high factor loading, that means if you have a strong relationship between variable and factor, it will lead to the higher commonality, common variance, okay? Right. And then now, so our package provide this information. So this is item complexity. So honestly, I never used this information. So I don't see any research using this information, but I don't know why R provides this information, but they are all 1, but something as 1.1. So that means it can go over 1.1. Okay, so here is the formula. Okay, so but I mean, we don't need to focus on this interpretation. Usually we focus on these things. Okay. And then let's talk about the loadings, and I will erase. Okay, so SS loadings, this is eigenvalue. Okay, so eigenvalue of the first factor is a 0.26, and eigenvalue of the second factor is a 3.12. Okay. And then this is proportion variance. Okay, that means 36%, right? So 36% of the total variance explained by factor 1. So how can we get this number? So this is common variance for, this is eigenvalue, right? Eigenvalue is the variance of the eigenvector, right? So that is variance. So this is our common variance for the factor 1. And then what will be the total variance in this case? We have 12 items, 12 variables. The total variance will be 12, right? So 4.26 divided by 12 will be 0.36. Okay. And then here, 3.12 divided by 12 is 0.26. Okay. So this is the proportional variance, and this is a cumulative variance. So you can simply add 0.36 plus the 0.26 is a 0.62, right? So two factors explain the 62% of your total variance. Okay. So, and then now let's see the proportion explained. Proportion explained, this is relative. This is a relative proportion. What that means is, so how can we get the 36, 0.58? This 0.58 is like give me a second. So this should be 0.36 divided by 0.62. So let me check. So is that, am I 0.36 divided by 0.62? Is that correct? 0.662 divided by what was it? Point 0.62 oh, I'm sorry. 0.36 divided by 0.62. Okay, 0.5. Yeah, 58%. So that is like, this is like this one divided by this one. So this is a relative proportion. Okay, it's 0.63 divided by 0.62. Okay, so that is 0.58. Okay, so this is relative proportion, and the rest of them is the proportion of the second factor. And then this is a cumulative proportion. Okay, this is how you can interpret your factor loadings, commonality, error variance, eigenvalues, and proportion variables. Okay. Okay, now your output provides more information. So this is the factor correlation. So 0.13. This is a correlation between factor 1 and factor 2. Okay, so two factors correlation is a 0.13. So it's a fairly low correlation between these two factors. Okay, and then this package provides more information here. So this is it provides some hypothesis testing that two factors are sufficient or not. So in this case, our null hypothesis, and also it compares the alternative hypothesis, but they provide the values and chi-square values. Where is it? Degrees of freedom and the chi-square value. Okay. So, and if you get it, so this is chi-square value and degrees of freedom of your null hypothesis. Enter it here, right there, and we will get significant result. Okay, that means our null hypothesis is two-factor. No, I'm sorry. So the restricted model, one factor, and it compares the restricted model versus the full model. So the one factor versus the alternative model is two-factor solution, right? So we reject our null hypothesis. So we reject it. That means, okay, two-factor will be enough. Okay. So the R provides, so FA, the package provides this information, but the other package, I don't think other package provides this information. So anyway, this is how you can interpret, and also, not here. It provides some RMSR, and then root mean square of a residual. This is what is that? RMSEA. Okay, so these are a measure of misfit. Okay, so we'll more talk about these measures in the psychometrics class, but the basic idea is that these are the measure of a misfit. Okay, we want a low value for the misfit, right? So the rule of thumb, if these value RMSL or RMSEA, if they are less than 0.06, that's a good sign. That means that there are not many errors in the covariance matrix. Okay. So the main idea is that we have a original covariance matrix, right? Covariance matrix or correlation matrix. Let's say this is original correlation covariance matrix, and then we estimate it using the data set, right? So this is covariance matrix, estimated covariance matrix, right? The difference between these two is residual matrix, right? The average of these residuals should be less than 0.05 or 0.06. Okay. Think about the regression, right? You have y ax plus b. You have actual y value and a y hat value. The difference between y and y hat is what? That's error, right? They're the same thing. Okay. So the RMSE or RMSEA, so are a measure of a misfit. So in this case, it's a good 0.05 and 0.06, that they are less than 0.06. Okay, so that's a good sign. The two-factor solution may be fit well with our data set. And then right here, and then another, oh, here is the RMSEA, right here. What is this? Root mean square, the residual. Oh, this is root mean square, RMR, I'm sorry. So this is RMR, but interpretation is the same. This is a measure of a misfit, and this is RMSE. This is another measure of a misfit, but this is a somewhat high because this is greater than 0.06. Okay, but we can interpret, we can consider other measures as well. So, and TLI, this is Tucker-Lewis index, TLI. Okay, this is almost a 0.87. Okay, TLI, this is a measure of fit. So we want these values greater than 0.90. At least it should close to the 0.90. Okay, 0.87 is a somewhat low, but I will say it's okay based on our clear the factor patterns. Okay, so even though it has a somewhat low the TLI and the RMSEA, but our factor pattern is so clear with the two-factor solution. So I would say, okay, this is fine. Okay. And now let's talk about, this is correlation. Okay, let's look at this one first. the multiple R square of correlation scores with factors. So this is just like the R square for the regression model of the items. Okay, so that means that your 12 items, the 94% of the total variance of your 12 items is 94%. So your 12 items explains 94% of your factor one. Okay, it's more like the R square in the regression model. And then this one, the correlation of scores with factors, that this is a squared R square. Square root of R squared, so this is R correlation. So correlation scores with the factors. And factor one and factor two. Okay, so we see a very high R square, there's a really high R square, right? That means our 12 items, 12 variables have a very clear the patterns and explains our total variance very well. Okay. And now these are all additional information. So like the, okay, residual and a chi-square value and some, right, corrected RMS value, SAVIC, fit measure, standard deviation factor scores, a number of factors, a number of observations, criteria. So these are all the additional information. So you can get these informations from here. So if you like the, okay, so let's say that we run 2-factor solution. Then if you see structure and PA2, right? And if you run it, I don't know why warning message. Okay, so you can see all different, well, detailed information, okay? So chi-square, RMSE, EBC. Okay, let's say you want to get some, but RMSE, you want the RMSEA, so maybe you can type. So your model is PA2, right? PA2, $, and RMSEA. If you run it, run it, so you will get RMSE information. Okay, so sometimes you may need more information about your R square. So maybe scores. This is the factor scores, right? This is the factor score information. So PA2, $, and scores. Run it. Okay, and now we got factor scores, right? We have, oh my gosh, so we have a factor one scores, factor one and factor two. Okay, so you can get more information using that one, and commonality too. You can get commonality, rotation method. I mean, these are all provided in the output, but if you want to get specific information, you can use that. But definitely you have to put $sign here. Your model, $, and these output. Okay. And then, so, okay. So these are the factor loading plot. This is before we rotation. Okay, before we rotations, the 6 items are plotted here. And this is a factor 2 and factor 1, right? But after rotation, these 6 items fit to the factor 2 second factor. And then after rotation, these 6 items fit to the second factor, right? So the 6 items goes on factor 1 here and factor 2. So very clear pattern. You can check with that. Then also, this is the factor scores, right? So you can plot this one. So 52, let's look at the 52. So his factor score is maybe, this is, let's say -3, and this is -3. So maybe his factor score is close to the -3 on factor 1 and -3 on factor 2. So that means he had very low latent traits on both factors. Okay. So using 12 items, we extract 2 factors, right? And then factor 1 and factor 2. The factor 1 is, what is factor 1? Oh, you're right here. Yeah, factor 1 is the performance goal orientation is factor 1. Okay, so based on this information, we can name they are performance goal orientation. And the second factor is a mastery goal orientation. Okay, because look at this, my goal is completely master the material presented in my class. So, and then they are all the same factor. I want to avoid learning less than it is possible to learn. Right? They are common factors. So how would you name this common factor? So I said, okay, this may be a mastery goal orientation factor because these items are measuring same construct. So you need to find the common name, right? So for his and his, look at the 52. He has his factor 1 score is -3, and factor 2 score is almost -3, right? So how can we interpret it? That means he has very low level of mastery goal orientation, and also he has very low level of performance goal orientation. Okay. So instead of using 12 items, we can interpret these patterns using only 2 factors. Okay, this is data reduction, right? So what about, how can we interpret the 50, maybe 54, right? So he has maybe, the moderate level of, factor 1, but very low level of factor 2, right? Questions? Is it clear? No question? Okay, so like this. And then I summarize the result. We have 12 items in this case, but in your homework, you have 12 variable, not items, okay? It was 12 variable, maybe so 10 variables or something. And then we have, the 2 items loads on the second factor. These item loads on the first factor, loads on the second factor, and first factor, and last factor. And then based on the common relationship, and you can name each dimension. Okay, this is exploratory approach. Okay, based on these items, maybe these items are commonly measuring these dimension. So I named it. Okay. So yeah, that's it for today. So do you have any question about your homework assignment? Have you started homework? Not yet? No? Yeah. So okay, let me talk one more time. So maybe. Okay, this is homework, right? You have a 15 criterion. These are 15 criterion. And your sample size is, where's the sample size? Do you have a sample size? Okay, I don't have a sample size here, but anyway, okay. So using this data, so this is job applicants data. And the first question is principal component analysis. You have a 15 variable, but please reduce the dimension using the principal component analysis, okay? So do you want 2 principal component or 3 principal component or 4 principal component or 5, right? So run principal component analysis and determine the number of PC, okay? And using it, and then justify your choice. So why did you choose a 4 principal component or 5 principal component, okay? And then interpret the PC. Let's say you find the full principal component, and based on the relationship with the components and each variable, maybe first component will be something, or second component will be interpreted as some, the physical ability, or, something like that, okay? And then examine PC scores, and then you can obtain PC scores like the factor scores, right? So you can obtain PC scores and interpret them in the context of the problems, okay? And then, for example, so what do you think about the applicants, the 40 and 42? Okay, right? So you can find the 40 and 42, and you can compare their principal components, like the factor scores. And then suppose a late comp applicant submits his the application after PCA. Okay, he got all 10. You built a principal component analysis equation, right? You run the principal component analysis, right? And then you can make a new data set using all 10 and predict. So what I'm saying is, do I have an example here? Not here. Maybe. Okay. Okay, I don't have that example. So what I'm saying is, first, you need to build principal component equation. You can build that, right? Based on you will have a principal component coefficient, and you can make an equation and plug numbers into the equation. Okay, does that make sense? or you can easily, you can do that, or you can use predict function in R. Okay, if you use predict function, you can find the predicted value. Okay, please review your the regression class one more time, so you can get for example, y equals, based on your equation, let's say I have, okay, this is my principal component equation, PC1 plus, and then I say, I'm sorry, PC1 equals 0.7 times x1 plus the 0.5, 0.6 times x2 plus the 0.1 times x3, okay? And that way you can have multiple equations, right? And then it says, okay, he has perfect scores, 10. So you can plug 10 here. Okay, that will be 10. So 10 times 10 times 10, that will be expected score for that applicant. Okay, I think that this is enough. So, and then the question 2, part 2, okay, they're using the same data. Now please run factor analysis. Okay, evaluate correlation metrics and plot it, and briefly describe the result, and then conduct a Bartlett test, a KMO test, to evaluate the suitability of factor analysis, and then determine the number of common factors to use. So how many factors do you want to use? 3 factors, 4 factors, 5 factors? Why? Okay, so justify your choice, and then use upper limit method and ML estimator. So in my example, I used the principal axis factoring, but for your homework, please use these methods, the ML estimation, okay? So how can you do that? So you can simply change like that, ML. That's it, okay? This is PA, this is ML, okay? If you wanna check, so you can always use help function, FA. And then you will see a lot of detailed information of a method, right? Where is method? Okay, you right here. Not here. FM. GLM. Oh, we are right here. ML will do maximum likelihood effect analysis. Okay. And examine common factors and interpret them in the context of a problem. Okay. That means you can interpret the factors, right? So, okay, for example, cognitive ability variables and some, maybe the factor one may explain some cognitive abilities. And you can say, okay, so factor one may be cognitive ability dimension, and then you can interpret the factor loadings. Right? So the variable, this one is highly correlated with this variable, and the factor loading is this one, and the commonality is this one, and the error variance is this one, and interpret that. Okay, and then get the common factor scores using the factor scores function, right? Like I said, where is that factor score? This is the factor score. You can get factor score. Okay, this is the this is the factor score. Okay, get the factor score and interpret it. What do you think about the applicants, the 40 and 42? And then last one, if the overall goal is to find the best application, best individual to hire based on the first two factors, that means you need to investigate the factor one and factor two. Okay, for example, okay, my factor solution is 3 factors, and just to focus on the first 2 factors. Okay, if you get 4-factor solution, just focus on the 2 factor. Okay, because you cannot visualize 4 factors. That's a 4 dimension. You cannot draw 4 factors, right? So using the first 2 factor, you can draw, or you can evaluate the factor scores, okay, and who are the best applicants. Okay, that means the higher factor scores indicates good performance, right? So you can find it. Yeah. And identify 4 applicants and report their factor scores of the first and second factors. Identify the highest 4 applicants based on 2 factor scores. And then last, so please describe what is the Kursor dimension and discuss why data reduction technique is important and needed for multivariate statistical analysis. And then compare and contrast PCA and factor analysis with some example, like the statistical algorithms, how they are different, or what would be the different practical implications or applications. When do you use PCA over FA? Or when do you use FA over PCA? Okay. Okay, so that's it. Any questions? The homework?
So I have a quick question.
Sure.
For EFA, we do the Bartlett test and KMO test.
Mm-hmm.
For principal component analysis, will those 2 tests can be used for that? Because it seems that they all need to be correlated to begin, so we can use the PCA and EFA.
Yeah, you can use this one for the PCA as the first step, but generally these are tests only for the FA, because when they developed this test, So they proposed this test for the F factor analysis, not PCA. But the PCA, I mean, we definitely expect a high correlation among variables, right? So, you can apply that. Yeah.
So for PCA, I can just say this is the correlation metrics, and it looks they're kind of connected to each other. Then I can just run PCA. Okay. Thank
And
you.
they are highly correlated each other. And yeah.
Okay.
You feel better now? I hope you feel better. No, I don't want to make you, hard. So let me know if you guys have any question. So if you don't have any question, I will stop here. Okay, so have a great week, and I will see you next week. So next week, we will talk about canonical correlation. That is another types of data reduction techniques. Okay, so have a good weekend. Bye.